Hello, I'm Craig. Let's talk about cars. So that last video kind of ended abruptly. I wanted to finish off explaining my Hall effect circuit here. So to recap, again, I have basically, think of this as like a, forgive my art, but I'm a mechanic, not an artist. The this dish, kind of three-dimensional, think about like upside down cup, and it's got notches on it. These notches go through this U-shaped device, which has a magnet and a Hall effect switch on it. As these vanes go through this window, as you see right here, this is a vane kind of looking above. As they go through that window, it's going to influence that Hall switch by the magnet. Is going to pull those electrons to one side, and that varies the voltage from 0 to 5, 0 to 5, 0 to 5. We last left off saying that you can have two sensors on that Hall effect. So it could be a 4-wire digital sensor instead of a 3-wire like we've been talking about. That fourth wire is just a second input. See this dotted line I had? That's going to alternate that signal. And the reason why they do that, let me erase this, whoops, to show you. What they do is they bring in another magnet right here and another Hall on the basically 90 degrees out, and then that comes up here and that becomes that signal 2-wire. Okay, so it's going to monitor those two positions. And why they do these two is so if this is going counterclockwise, the computer is going to get this signal first, this signal second, and they're going to be offset. If I change the direction of this and it goes this way, it's going to get this signal first and this signal second, and there's going to be a gap between that. The computer can use that information to determine direction and speed. And so when we're diagnosing this, we keep it simple. I need battery voltage or 5-volt reference, depends on the signal. At the switch, I have my two signal wires, which I want to make sure they look similar to this on an oscilloscope. This is voltage over time. And I want to make sure I have 0.1 or less on the ground wire. So that's basically your Hall effect, in a nutshell, your digital sensor, your 3 or 4 wire. So with this video, we're going to show you is how to diagnose outputs. So all outputs by the computer, I can say all of them, but most of them, the ones we care about at this point, are like I mentioned before, either a high side or low side driver. And what I mean by that, let me move my circuits here. I'm going to take this stuff out of here, take my switch out. What I mean by that high side or low side driver is if I have a solenoid, okay, I have a solenoid, it's going to either be operated given power or ground. Agreed? One of them needs to be given. So if I have the PCM up here, it's going to have a transistor up here that's going to operate it. Now, for sake of this video, to make it simple, I'm going to put it as a switch. Okay, it's not a switch, it's a transistor, but it works as a switch. The computer controls the base, the switch turns on, and then it sends power to your control device, and it's grounded. Or you're going to have, you can have battery voltage, a fuse, go down to your solenoid, and then that goes down to a computer, and that's going to be a switch inside. So the computer signals the base, and that controls a switch to ground the solenoid. This is low side driver, this is high side driver. So these switches right here that I draw in, these are transistors in real life in the computer, but transistor, like I mentioned before, is kind of like a relay and a switch. It's the way the computer can turn on or turn off these devices. So the computer circuit board signals the base. It's got 3 wires on this transistor. It's going to signal the base, and that allows current to flow through, much like a switch, right? We operate a switch, and the current flows through. So this computer operates the base of this solid state device, which just means there's no moving parts, and it allows current to flow through. The more current it applies, the more current flows through. That's why it's like a relay. A small amount of current controls a large amount of current. Okay, now ignore that part for now and just think about diagnosing this. If I have a solenoid that's controlled by a computer and it has a known a fixed ground, we know that this is always going to be less than 0.1 volts, right? And this is going to vary between either 0 and 12 or 0 and 5, on and off. So when I measure right here, I want that to be 12 volts, let's say, when it's operating. So that's why I tell you to diagnose it like a switch. If this transistor is off, I'm going to have 0 volts. If it's on, I'm going to have 12 volts. Over here, I have 12 volts all the way through the circuit to open if it's off. So on this side of the circuit, it's always 12, just like this side's always 0.1, this side's always 12. This side, since this is the side that's switched, this one's going to go from either 12, it's either going to be 12 or 0.1. Okay, this is going to be 12 or 0, right? Based on position of the switch. Again, if this switch is open, I get 0 volts. If it's closed, I'm going to have 12 volts coming through down to the solenoid, 0.1 or less afterwards. On this circuit, I always have 12 up to the solenoid, and then on the ground side of the solenoid, I'm going to have 12 if the circuit is off and that transistor is open. If it's on, I'm going to have 0.1 or less according to Ohm's law, right? So we diagnose this accordingly in the car, and I'm going to do that real quick, make it simple. Let's do this switch. Pretend this is the computer right here. Okay, so this is the transistor in the computer, and I'm going to operate my solenoid. This is going to be my device, okay? And I'm going to have a ground right there. So it works just like this is a load to ground, okay, right here, this circuit. So you see, you hear it, and you kind of see that little thing moving. So you can move this back over here. Kind of hard to see. I'm going to go ahead and switch it out for a light. Just trying not to do a light because it makes it bright. It's kind of more obvious, so we'll do a light. Going to have to run my little thing here to keep it down. So if I operate, whoops, I got to go up to my, all right. So here you go. Technical difficulties. This is live. Take one. All right. So this circuit on my left is indicative representative of this schematic right here. Okay. Just I replace the solenoid with an incandescent bulb. And this is perfect because it doesn't matter what the load is. The computer doesn't care. All the rules are the same. That's what's beautiful about learning physics and theory and how this stuff works. You can diagnose it all. So I'm going to pull up my meter and let's measure up here. Coming out of the computer, I got what? 12 volts, just like we thought, right? With its on. And right here at the load, right there, at this point, right there, 12 volts. If I turn it off, it's going to be 0. That makes sense. This is obvious, right? Well, it's obvious on the computer as well. Of course, it gets more complicated than this, but this will carry and diagnose 90-some% of all your faults you're going to need. The computer can also monitor current, but we won't get into that in this video. Just if you see a schematic that shows the computer controlling the power, diagnose it just like it's a switch above and the load to ground like we diagnose those. So like right here, I'm going to measure 0.1 or less, right? And that's what I got. That's right there, 0.1 or less. Okay, so get really good about writing what you're expecting in order to know what's broken. Again, you can't know what's broken unless you know what's normal. Now this circuit over here, let's go ahead and draw this one. And that's going to be, or replace it with incandescent bulb as well. And again, it doesn't matter. That's the beauty of it. I'll turn this off. We'll move this over here. And this is just like what we did in class. I'm going to run that right there. And then there you go. So that's this circuit right here. The computer is that switch. So right here at the computer, remember, pretend that switch is in the computer. That's the transistor. It's going to be 12 volts while it's off, right? Just like we mentioned earlier, right here. Okay, we have that 12 volts while it's off. All right. If I turn this switch on, this transistor turns on, what's going to be? 0.1 or less. And I got 6 millivolts. That's 0.006 volts. Bingo, or less than 0.1. So this is working exactly how I thought it would work. And so diagnosing is appropriate. Let's say our ground's open. Computer doesn't have a ground. Of course, the computer was shut down. I'd have nothing working. Let's say we lost a fuse. Of course, I have 0. That stuff makes it kind of obvious, right? If I had unwanted resistance in here, I'm going to have, basically not going to get full battery voltage to that load. And I would see that if I measured at the load. Right now, I'm getting less than 0.1, like I should, which is right here. I got less than 0.1 right there. If I had resistance in the circuit, which I have my resistor still, this is if I had like a bad wire. Okay, well, that's too bad. Let's get us less of a bad wire. Let's see if I can, it's kind of glowing, look at that. I need to find a smaller resistor. Nope, that's all I got. That's the smallest resistor I got. You can kind of see it glowing in there a little bit. What's happening is the resistor's too high, not enough current. And look at my voltage. See, 10 volts. And I'm measuring it right here. Okay, right there. I got 10 volts. I should have 0.1. That's telling me there's resistance downstream. So we use the voltmeter and measuring voltages throughout the circuit as text to figure out what's going on. Like right here, I'm supposed to have 12 volts. If I had 10 right here, I know I have resistance upstream, right? So that's kind of how we diagnose these circuits. Again, this is just basically you're diagnosing these outputs. This can be a light, it could be a solenoid, it could be a fan, it could be any output the computer controls. High side driver is diagnosed just like a load to ground, and then a low side driver is diagnosed like a switch to ground, like you're taught in class. Okay. The other thing I want to talk about in this video is duty cycles. Some devices aren't turned on and off; they're pulsed. Like let's say this was an LED. Let's turn this. Let's change this to an LED circuit. So here it's coming down. We're going to have, a resistor, and then we're going to have the diode and our little arrows. Okay, we'll oops, kind of hard to do with the marker, but basically this is our LED setup. Okay, and it's going to go to ground. So there's our LED setup. Like let's say dash lights. Okay, so LEDs can't be dimmed, right? They're either on or off. So how do we simulate a dim LED? We pulse it, and that's what's called duty cycle. So this switch, remember the transistor in here, instead of being on or off, either being 12 volts or 0 right here, like if it's on it's 12 volts, if it's off 0, I can simulate 6 volts by duty cycling it. So let's say I want it to be 6 volts. In an incandescent bulb, that would just make the light dim, right? Well, I can't apply 6 volts to an LED and have it work that way. So what I do is I take the 12 volts and I duty cycle it. Here's how. Here's my voltage over time, much like we were talking about Hall effect. Here's 12 volts right here. I'm going to have 12 volts on 50% of the time and off 50% of the time. So this is your duty cycle. Okay. If I take it and look at it a cycle, here's one cycle right there. We'll dash line it. That section, you can see that it's on 50% of the time and it's off 50% of the time. That gives me a 50% duty cycle. And it's going to make the light dim. It's going to be going really, really fast. So it's a higher frequency. These are cycling 1,000 times per second. They're going fast. I don't know what each component is, but it's going to be cycling so fast, our eyes can't see the LED turning on and off. That's basically what's happening. It's turning on and off really fast. It happens to go really, really fast where our brain can't see it. When we see the 50%, it's going to be on half dim. If I want it to be on longer, I can run a 75% duty cycle. I increase these to where they're on 75% off and off 25%. That changes it to a 75% duty cycle. So again, to diagnose these circuits, you can use a voltmeter. It's going to give you a percentage in here, but more accurately, you should use a DSO, digital storage oscilloscope. You can see the duty cycle of that. If I want it really dim, then I do a 25%. So I turn this whole section off like that, see? So now it's on 25% of the time, off 75%, and that gives me a real dim LED. So that's basically duty cycle, is how much on and off time it is. And again, frequency is how many, this is a cycle, right, between these dashed lines. How many of these cycles happen every second is hertz, and that's your frequency. The higher that is, the brain can't see it. And so that's how this system works. But again, we can diagnose it accordingly. If I measure my voltmeter here, like let's say it's at 50%, my voltmeter is going to average it. Let's turn this back to 50. Computer sending 50%. It's cycling this switch on and off 50% of the time. My voltmeter will actually average it, and it's going to show me 6 volts. So you can do it that way. You can adjust your meter to show a percentage of on time, off time. But again, my favorite method is using an oscilloscope, which gives you a display, a picture of that duty cycle. And this is kind of how it controls. You can control lots of stuff: motors, lights, LEDs, anything you can dim. That way, this is how the computer can control something variably. Okay. because the computer